Yeah, thanks a lot. I'll say in advance that this should be like a fairly non-technical talk. I'm not going to really be presenting on any of my own work. This is very much work in progress. I'm like writing a position paper, rant, whatever you want to call it. I don't know. It's basically some random thoughts. This is kind of in conversations with Florian Tremere so far, but I didn't put his name on this because if there's any hot takes, those are I don't want to put the blame on him. So yeah, this should hopefully be short and light. So private machine learning is a big deal nowadays, and it roughly asks the question, given a sensitive training data set, what accuracy can we achieve on a test data set under the constraint of differential privacy as applied to the training data set? And as most commonly done, I'm going to be focusing, like there's many ways to do this, but I'm going to focus mostly on when you train a neural network using differentially private stochastic gradient descent, which is kind of the most common way of doing this. I have two slides on what SGD and what DPSGD are. I'll look at it quickly just because we might not all be super familiar. Usually most neural networks, despite the fact that this doesn't necessarily have provable guarantees all the time, most people train neural networks via SGD, where you select a random mini batch of points, take the gradient, take a step in the direction of the gradient, repeat. Very simple, very popular, well used. For the differentially private setting, it's pretty much the same thing. There's a drop-in replacement, which is exactly the same except for, well, mostly the same except for two little differences. One is that you have to clip the gradients individually. That's natural because you have to limit the sensitivity. Otherwise, the gradients could be very large. So like this, if your gradient is this thing C here, then, or sorry, if your gradient is the black arrow here, then you have to clip it so that it's not too big. And then the other thing is, of course, you add Gaussian noise, which is our favorite, the Gaussian mechanism. Yeah. So essentially, it's just SGD, except you clip in noise. Very simple, very plug-in, drop-in replacement. So let me tell you, this has been like what people have been doing for the last several years. I guess people really started focusing on DPML in this way, at least since 2016, probably a bit earlier, but a lot of the practical advances have been in the last 5 or 6 years. And let's see how we're doing so far. How has the community done? The first thing, whenever you do an ML task, a common thing to start with is MNIST. MNIST is very simple. It's black and white image classification. Say like you have to, these are the inputs, they're 28 by 28 black and white images. You have to predict what number it is, 1, 8, whatever. And so this is a canonical easy ML task. Whenever you're doing machine learning, like if it doesn't work on MNIST, then like maybe something's going wrong. You have to make sure you pass this test, say. And in the non-private machine learning setting, it was solved like whenever it was invented, the day after. You get effectively 100% accuracy. And privately, you get epsilon 1 to 3, you get 98, 99% accuracy. This is in, say, Tremere, Bonnet. Yeah, we can do pretty well on MNIST. So I would consider this as like, this is solved. We're good. We passed the sanity check. All right, that's like machine learning 101. What about machine learning 102? Like, what's the next step after MNIST? In the context of image classification, people generally turn to CFAR 10, which is a bit different. It's a bit more difficult. It's low resolution images. It's like the pictures are roughly the same size as MNIST. They're 32 by 32 instead of 28 by 28. They're kind of low resolution. They're blurry. Yeah, you can kind of see them here. This is like, these are horses, these are cars, planes, and so on. They can sometimes even be hard for humans to tell, to be honest. But yeah, and of course they're colors, so they're 3 channels, so they're kind of 3 times the number of features. So this is roughly the same size as MNIST if you ignore this factor of 3, but it's much harder because a 0 is very clear what a 0 is, but these it's not quite as clear. Like all dogs kind of look quite different. So it's a harder task. Nonetheless, non-privately, you can do pretty well on this, say 98% plus. But privately, here we face a huge problem when it comes to accuracy. The accuracy drops from say 98% plus, so like 2% error to 30% error plus. So this was again in Tremere, Bonnet, and there's been a few more recent results. If you weaken the privacy guarantees, getting up to say 73.5% for epsilon equals 4, 82.5% for epsilon equals 8. They're getting to weaker and weaker privacy guarantees, and there's still like 8, 9, or 10 times the error increase than compared to what we had before. So it's like it's kind of disappointing because we did well on the very first task you would consider under private image classification. But the second task, it seems like we didn't really do too well. Someone was discussing this paper on Twitter, and you know, the privacy community was like really lauding, oh man, that's a really big improvement from what we had before. And then someone who's not a private ML person commented on like, wait, are you guys still on CFAR? Like, and I don't know if I justified, but maybe me or some other folks had to justify like, this is a big deal because we didn't know how to do this. This is hard under privacy. And then there's even harder things. For example, ImageNet, one of the big things which has been like the rise of deep learning back in 2012 was when we finally could do good classification accuracy on ImageNet using deep networks under AlexNet. This is like a hard data set. These are like much bigger resolution pictures. There's many more classes. There's many millions of images as opposed to the previous ones, which were in the tens of thousands. There's thousands of classes as opposed to just 10 classes. So this is like the big leagues. And how do we do? Well, non-privately, you can do 87%, say if you want to do top 1 accuracy, meaning you have to get the right label perfectly. But if you look at privately with even epsilon equals 8, we do not do well, like 32%. I'd say this is already very, very impressive, but like this is not, any practitioner in the non-private setting will laugh you out the door if you show them 32.4% on ImageNet. I tried to find some historic data, but I couldn't find I don't think there's, I think the first state of the art for ImageNet was probably higher than this, but I'd have to double check that. So yeah, when it comes to, you know, the big kids table, it seems like we had to put in a lot of work and we got like 32%. So the story so far that I'm trying to get across is that private machine learning seems to be hard. It needs a lot of work in engineering to get reasonable accuracy, which might not even be reasonable a lot of the time. And even then, like I said, practitioners are not impressed. You're not going to be able to convince someone to deploy this ImageNet with 32% accuracy. They're not going to waste their time on that. So let me show you how we can potentially recover from this, you know, big blow to accuracy. And this is what's known as pre-training. This is kind of a big thing nowadays in the non-private literature and growing in the private literature. But the idea is, first of all, the first step you do is first you pre-train the model on a very large, diverse, lightly curated data set. Roughly speaking, you can imagine the following type of procedures. Not exactly this, but if in your head you can picture, you download everything you can find on Google Images. Maybe you take whatever text and you associate it with the image. So it's going to be like random pictures from whatever different sources. Maybe there's some text which is related. Maybe it's not perfectly related. Sometimes you can even do away with labeled data. What's known as self-supervised learning. This is popular. I'm not going to get into what that means, but sometimes you don't even need labeled data and it still works well. And after you pre-train the model very like kind of using this huge data set, which is not high quality, then, oh yeah, maybe to give you some idea of what self-supervision might mean is like, if you have a sentence, then maybe you make your own little learning problems where each time you're trying to predict the next word. So you don't have any like explicit labels, but you find the structure of the language by being able to predict next words. That's a natural thing you can do. So hopefully that gives you an idea of, you know, how you might be able to use just random data in order to do something. But after you do this pre-training, then maybe you specialize the model to whatever task you care about. Say, if you want to do CFAR 10, maybe you fine-tune the weights of your model. That is, you basically do gradient descent, but changing with maybe a lower learning rate. And you update the model based on the training set for CFAR 10. And this is kind of the predominant framework for large-scale ML problems. If you've heard of, you know, GPT-2, GPT-3, BERT, even if you're not super familiar with these, this is kind of how these are generally used. They're trained on large, diverse data sets, and then they're specialized for specific tasks. So this naturally, I know there's going to be some complaints about this, but this naturally lends itself to differential privacy, because you can imagine that you first do the pre-training procedure on this large, diverse, lightly curated, and public data set. I've used this air quotes or quotes here to appease perhaps some who will raise concerns, and we'll revisit those in a bit. But the idea is like data generally scraped from publicly available sources, so maybe this data is kind of public in the sense of not having a privacy violation. Maybe we'll revisit that. But after that, then if you have a specific private data set that you want to fine-tune on, then what you do is you privately fine-tune the weights using DPSGD. So to show the distinction, I want to do the first step exactly the same as in the non-private setting. No need to worry about privacy there. The second step, we're going to use DPSGD to maintain the privacy of the sensitive data set. I'll pause just briefly here for questions in case anything's unclear about the sort of setup and the paradigm. Cool. Okay. So why is public pre-training useful? I haven't told you how useful it is yet. We'll see that in a sec. But the way I think of it, this is all deep learning, so whatever post hoc justification you want to give, you can. But the way I think of it is that it seems like pre-training generally learns useful and general features for images, and then fine-tuning combines them to do the specific task. Like basically, you get some picture, and then first you're going to find a bunch of different useful features which might be useful for future tasks down the line. But like if you do this fine-tuning, then we say, okay, we've got all these different features, so let's combine them in the right way to detect, say, COVID chest X-ray pictures, which might be, say, sensitive in this example. Yeah, Roy. Is there a question online? Oh, a hand raised by. Oh no, that's yeah, that's funny. I see. Yeah, it's this mouse right here. No more hand raised. But okay. So my weird hot take here, which might be a little bit an odd perspective, but my claim is that doing private ML without any supplementary public data set is like pretending that we have no idea what photos look like. If you just start from scratch and you don't do any pre-training, then kind of your network starts being able to indistinguish between these two pictures. As like we know that this is a real picture and this is just some garbage, but like if you start with a neural network without any pre-training, then they kind of both look the same at that point. Another thing I'll say, we didn't focus much on language models in today's talk, but I'll say if you don't do any pre-training and you try to do language processing privately, you're kind of pretending that the entire English language itself is private, which of course it's not. Basic syntax and grammar is not something we want to protect the privacy of. So maybe this privacy issues aside, we'll talk about that. I claim there should be always some sort of pre-training of some sort. But anyway, this is like the intuition of why it should be useful. And let's see how it helps. And there's huge gains using public data. So this is this nice recent work by De et al., where the top line is without using any public data. And you can see these are the numbers I kind of quoted you before. But if you pre-train on ImageNet, which we know is a much bigger, very diverse data set, you can see that we can get like 95, 96, 97% accuracy, which is like not embarrassingly bad. Like remember, the non-private benchmark was maybe like 98% plus. So this gets back into the realm of something where practitioners won't laugh you out the door. Yeah, and so we pre-train on ImageNet, fine-tune on CFAR10. So it seems like here, this pre-training and public data seem to help. And let's go on to the big league. Let's talk about ImageNet. And for ImageNet, it's even more dramatic in the sense that if you do this, yeah, here's a bunch of different plots. So this first line here is what I quoted you. If you don't have privacy, sorry, if you only have privacy and no public data, then 32.4% is what you can get. But if you pre-train on some data set, which we'll talk about a bit more later, called JFT4B, very mysterious, but you can get up to very high accuracies relatively of like 86, 87%, even at very low privacy budgets. Like how many things can you do at epsilon equals 0.1? You can apparently learn ImageNet, which is one of the hard ML tasks, at 77% accuracy compared to 90, 91% non-privately. So you can see by using this pre-training, we can get very close to the state of the art, even without privacy. And all you have to do is pre-train on this mystery data set, which I'll revisit in a few slides. And because I feel like some obligation to say I did something and I'm not just like ranting at you, we did some work on NLP, but I want to keep it focused on image classification so that we don't get distracted. Cool. So the takeaway so far is basically that using these public data sets is massively useful. Like it can give you these huge gains in accuracy, and it's embarrassing to not use it in some sense. And I want to tell you about another concept which is popular, kind of, I think, the sort of natural conclusion of pushing this idea to its limit, which is what's known as zero-shot learning, which is essentially the same thing as before. We first pre-train the model on a very large, diverse, slightly curated data set, and that's it. No step 2. Like, just feed in the test data set. You don't need the training data set. This, for example, like you could train a model on this, say, JFT data set, and from there, you don't fine-tune the weights, nothing. You just ask it to do some other task, which is seemingly not super related, and it still does really well. This is a surprising fact to me personally, but it seems that some extremely large models can do well on tasks without fine-tuning on a task-specific data set. And this is a big buzzword in non-private ML. It's not like it's emerging. There's some zero-shot capabilities of certain models. It's not like everything is doable without any fine-tuning, but there's been some big advances and people are excited about it. And so my claim is that actually the state of the art that I claimed in the previous 2 slides ago on ImageNet is not the state of the art if you consider this paradigm, because here is a paper by some non-private ML people. So Kwok Lee runs the group at Google, which they do some very, very large-scale machine learning. And this is a portion of their abstract. They achieved 85.7% top 1 accuracy on ImageNet validation set without learning from any labeled ImageNet example. So to rephrase that for the privacy community, in some sense, what they did was they achieved 85.7% with epsilon equals 0 differential privacy. That's in comparison to the previous thing where it roughly matches at epsilon equals 4. And I think, you know, ignoring the fact that I've still swept some privacy concerns under the rug, but you know, getting epsilon 0 versus epsilon 4 in the same accuracy, that's like a much stronger privacy guarantee in some sense. The data set in this is not exactly JFT4. It's like JFT, which I mentioned before, which was like what this Day et al. Used for this, and some other stuff and some other processing. They did some other tricks on the pre-processing. This is like a 60-page paper. They do a lot of engineering stuff, but it's roughly the same sort of paradigm pushed to its limit. Stephen has a question?
Yeah, so is the model directly applicable to ImageNet? There's no like realignment of the labels,
Yeah,
details?
I think they don't need anything specific for ImageNet. Like literally you feed in the ImageNet test set and it'll do something. You feed in MNIST and it'll do something. You're right in the sense it doesn't even have the labels. I can't remember if they like output text things which are similar. Maybe you have to specify what the labels are, like because you know the labels.
Maybe they partition the data into abstract labels. They don't need to know what the label is. They don't need to know these are fish, but they know they belong to the same class.
I don't think so. I think maybe you could be right, but it also has some idea of what a fish is just from this massive pre-training set.
That's true.
If I had to guess what the model is, if I had to remember, I think they basically specify the set of 1,000 labels and then just chooses how to associate them. So you have to assume that the labels of ImageNet, what you're trying to classify them to, is public data. But that's it, I think.
Okay.
Yeah, Roy?
Again, the follow-on to Stephen would be, does like this, the only way this work is if like MNIST is somehow within the data set that the very large data set that was trained, or if we're taking this to privacy land, do you, like, and you're talking about medical data, which maybe we don't have a giant public data set that is specifically medical. Like I'm asking that the thing you're applying to being within distribution versus out of distribution.
Yeah, I don't fully get your question. I think there is like they do discuss in this paper there are some issues of distribution shift. For example, this model, if you take it, it gets like 40% accuracy on MNIST. So like remember that's the easy task. But so there's some questions on how to do to make a distribution shift correctly or like make sure things are right. Like I can believe in whatever pre-training set there are the numbers 0 through 9 like very isolated because of a huge diverse thing. But I think there's some questions still on how to make things transfer well to specific data sets. That's still an open question in non-private land. Cool. One question from Shubhankar back there.
I was just wondering how would the last layer of the neural network work? Because like if you're training on something which has more number of classes or the classes are very different from what's in the private data set, like the first class could mean 0, but in the private data set, the first class could mean 4. So how would it work?
Yeah, so that's a good question. Basically, like in the conventional or more classical setting, you typically have to know what the labels are ahead of time. But a more popular thing nowadays was known as multimodal machine learning settings, where the idea is it doesn't only learn, say, the pictures and associate them with labels, it kind of matches labels and text descriptions at the same time. So it's kind of able to match things up even if they're not the exact labels. My knowledge of this is not expert, but the idea is somehow based on the vague text descriptions, like if I give you a picture which is a picture of a cat riding a tricycle, somehow it'll be able to extract from that okay, somehow this picture is associated with cat and tricycle and stuff like that. So yeah, somehow labels aren't super important nowadays, and they can be more freeform. Cool. So yeah, it seems like zero-shot learning is really surprisingly powerful. It's not like here in solving everything, but it's coming. Now let me revisit one of the things I hinted at before. I was mentioning, okay, you have to do this pre-training on JFT. What is JFT? Yeah, JFT4B. What is JFT4B? I didn't tell you. And this is some proprietary Google data set, which consists of billions of image text pairs. But basically, both of the papers, all of the papers I've referred to so far actually have been Google or DeepMind. So they're all like, they're the only ones who own this like very big data set, which is very all powerful, and no one else can touch it. So you might be arguing that this is not public data because, like, how did they get it? What are they doing with it? My understanding actually is it might just be a Google image scrape with some proprietary text descriptions, but I'm not sure. Like, I haven't gotten a good answer to that yet. But either way, this is not a public data set. So you might be thinking, okay, this can't be considered public data in any sense of the word, because not even publicly available. But there's data sets which are coming. For example, here's a data set called Lion, which came out like 3 weeks ago, or they had a smaller version. But this is a 5 billion like image text description data set. So the point I'm trying to get at here is this very large, powerful data set JFT seems to be useful. And maybe it's not public, but there's other data sets which are public, and there will be more in the future which are like this. I'm guessing like in a few years there's going to be Lion 50 billion or something, which is even bigger, even better at getting high accuracy for these sorts of things. And yeah, all these zero-shot models are going to get better. People are going to be getting better in the non-private setting and so on. And here's my like big statement. My prediction is that classic ML benchmarks will inevitably be solved via zero-shot learning using publicly available data, giving epsilon equals 0 with respect to this sensitive training data set. And the question is, what does this imply for the private ML community? And will we be out of a job? I mean, I don't know how many people here have been, I think this is like the first talk about DPSGD and stuff. So maybe everyone else will keep a job, but like this is kind of the question. What does this imply for the field? Because I think it's interesting and we'll be here sooner than we expect. So the rest of the talk, I'm going to give like some perspectives on this. Again, this is very much work in progress, so happy to talk about this more later. There's of course a natural question which I've been hinting at, is this really private? These are large uncurated data sets. And a natural question is, do they contain your secrets or secrets about you, to quote Frank McSherry's blog post. I thought it was a neat way to distinguish. DP is generally intended to protect the former and not the latter. So your secrets is kind of like often what DP is designed to protect, which is like things like, this is a paper by Carlini et al. And from a blog post by Wallace et al., where they found, say, GPT-2, which is pre-trained via some of these large uncurated data sets. They found, I guess this is not what I'm looking for. They found things like this, where if you prompt it, then it'll spit out some memorized text, which is personal information, someone's contact information. So this seems like personal in one sense. It was also trained on things like GPT-3. Apparently, somehow, though it was maybe only using publicly available data set, was trained on, apparently, text of Harry Potter and the Philosopher's Stone. So if you prompt it with the bold text, it'll spit out essentially a whole page of the book. So clearly, somehow, this data, which I sort of claimed before is public data, is clearly not public data because this is copyrighted. It shouldn't be things that are used here. So there's some question. The first question I'm raising here is, in these large uncurated public data sets, are they actually public or just like publicly available? And what is stolen? Yeah, sure. This, I guess, would be stolen. This would be maybe something someone revealed as public, maybe at some point. maybe inadvertently? Was this the actual individual themselves? This is just blanked out by, like, this appears in the clear in the model, but the authors of the paper made sure it was redacted. But yeah, at some point the privacy was like lost, and why did that happen, and what does that imply? There's also things about secrets about you. For example, we all know the secrets smoking causes cancer, and we don't consider this really a privacy violation as sort of the DP community. But I think like this is still kind of creepy, and people I don't know, there may be more privacy concerns about this sort of unexpected inference just given the availability of big data, which I think will make people uncomfortable about privacy, and so just something to think about in my opinion. So like, as I think this is my last slide, but the question is, how does private ML stay relevant? Is the community out of a job, or like what points are we still interested in, and what is there still left to do? Let's just assume my sort of prediction is that zero-shot learning via large public pre-training is pushed to the limit. That is, people deal with all these sort of distribution shift issues, and they can figure out how to make things, how to handle those things. I think there's still a lot of things for private ML to be done, to do. In particular, model personalization, which inherently is not you can't do it zero shot because it's supposed to personalize to something. So you need training data or else it can't do it. For example, imagine there's something which is generally good at handling email-based data, but in-house you want to specialize a machine learning model to your employee data sets. That's something which would need to be done, say, privately. There could be entirely new concepts for which public data does not exist yet. So there's no way you could have learned the concept because it's a new concept. For example, COVID chest X-ray pictures. Maybe you'd still need to do some private fine-tuning for things like that. There might be high security settings which may disallow public data. For example, I don't know. I can imagine there's certain restrictions at the census which would disallow, massively scraping public data. But also other things, if it's like system critical, putting in uncurated data sets like this would allow all sorts of bad things to sneak in. There could be backdoors or something. This can be seen as a dangerous thing to do. And reliable machine learning is still a very active field where it seems like the problems are bigger than the solutions at the moment. Oh, sorry, this is my last one, I think. Maybe we should focus on more meaningful benchmarks for privacy. I mentioned ImageNet. This is an image from ImageNet. Did I just violate this panda's privacy? Like, this is somehow, yeah, there he is. He's upset about it. This is in some sense a very like innocuous application. ImageNet is 1,000 classes of things which are like, different breeds of dogs. Maybe we should be focusing on benchmarks which are more specific to sensitive data sets, or more similar to sensitive data sets, so that if we actually care about something which is proprietary or privacy sensitive, then like we're already prepared, rather than maybe ImageNet is just silly because like this is nothing is sensitive here. So in closing, this is a question I'm asking to the community. What are the implications of the power and availability of large public data sets? What does this imply and not imply for privacy and differential privacy? Thank you.